Yeah, this is a protected
Hello and welcome back to Calculus 1 after the long and dreaded weekend, right? We are back on our regular calculus grind. So, related rates, part 2. We are going to take a look at a few more examples to make this more fun, I guess. Another problem relating cone. So last time we ended with the cone, and today we're just going to continue. So this is problem 29 in a textbook, draining a conical tank. So they have a tank like this, and then there is some kind of liquid inside, let's say water or whatever, and they want to drain all of that out. It says an inverted conical water tank with a height of 12 feet. So the height is 12 feet and the radius 6 feet. Is draining at the rate of 2 feet cubed per second. Now, what is the variable then for this if we are losing liquid like this? 2 feet cubed per second. So what are the units here? What is the, sorry? dV/dt, very good. We are losing volume in time. So loss of volume in time is going to be dV/dt. We could also put -2 because we are losing stuff, but then we can also pay attention later and just write. What is the rate of change of the water depth when the water depth is 3 feet? So H equals 3 feet. And what is the rate of water depth? So that's also going to be, that's going to be feet per second, right? So what is the rate of change of water depth? That will be the height of water, right? When the water is 3 feet deep. So we start this problem by writing the volume of 1/3 base times the height, right? The volume of the cylinder, the cone. But then we realize that we have, so this is the volume for water. So this age is the age of water. In a tank. So this is 1/3. Base is pi r squared, and then we have height. You have to understand that radius is changing because as the level of water is going down, the radius is getting smaller, the height is getting smaller. So both are variables. And I will take the derivative of this in respect to, so this is pi over 3 r squared h, and I will take the derivative of this in respect to time to find the related rates. So that's dV/dt is equal to pi over 3, and now I have a product rule. So copy the first times derivative of the second plus copy the second times derivative of the first. We have to keep them all as variables because they're all changing. And now, yes?
R squared dh over what?
Why I said that's supposed to be dt. that was a question. Yeah. That was supposed to be, I'm not sure why is the 2 there. Oh, I was already taking the derivative of r squared in my head while I was writing this thing. Anyway. It's called lag. For those of you who game. R is changing. Look. R on top is 6, right? When water is here, R is smaller, then smaller, then smaller, right? R is keep getting smaller every time. So now we have way too many of these. I know we are looking for this one. So that's the one that we need to keep. This one over here we don't need. They're not asking us about the change in radius. So now we are going to relate these guys. We know this is 6, we know this is 12, and we know that the radius r and height h of the water are changing. Those are variables. So from here we can say that 12 is to height, what 6 is to r, and then we can say 12r is equal to 6h, from where h is equal to 2r. From there, if we differentiate in respect to time, we have the relationship between dr dt and dh dt, so we can eliminate dr dt. So dh dt is equal to 2 dr dt. So now I already have 2 dr dt, so I can just replace all of that. So now formula is dv dt is equal to pi over 3, open parenthesis, we have, we don't like that r, right? So instead of r squared, we're going to write the back with the h, which is 1/2 h squared dh dt plus h, and then you have r, which is again h over 2, and then dh dt. It's hard to see, but r squared is replaced because from this equation I have that r is equal to 1/2 h. So I'm replacing r with h. I want everything in terms of h because I have no information on r of any kind. So I'm replacing all r's by h because I have equation that connects them. The one on the left connects h and r, the one on the right connects the rates. So now I'm replacing every r with h and every dr dt with dh dt. And as you can see on the equation on the bottom, there's no more r's anywhere, and we can solve the problem easily. So now dv dt is equal to pi over 3. This is going to be h squared over 4 dh dt plus h squared over 2 dh dt. So now that's 1/4 and 2/4 is 3/4. So dv dt is equal to pi over 3 times 3/4 h squared dh dt, and then these 3's drop. And now I have the model for the problem, finally. Pi over 4 h squared dh dt. Now they're asking for dh dt. We know that dv dt is 2. That's given in a problem. We have pi over 4. We have h squared. Now h, they said it's 3 feet. So that's going to be 3 squared. And dh dt is what we're looking for. So that's 8 over 9. So that's 8 over 9 pi feet per second. So your homework and your quizzes and stuff will have the same problem except different numbers, obviously. Yes.
So, like, on the homework, you know, it will ask for like the first equation, like relate the following to whatever, and then like the second thing. Like, can you just like label which one's which? You know, like, what's that final one called?
Yeah, because the homework will ask like different sequences. You know what I mean? Like different steps
Yeah, it'll
along
ask
the way.
for like your one there, the pi over 3 over square root of that thing. It'll like ask for that, and then the final one. You know, so.
Well, they will have to ask for the answer somewhere, which is this, right?
Yeah, the final answer.
Yeah, that's the final answer. So before that, you might. I mean, this is where you took the derivative, but it's not a final version because you still have both r and h here. I would have to read the problem to see exactly which one is which.
That's probably the relate R and H equation.
No, relating r and h equation is this one. This one over here relates r and h, and then this one relates the rates of r and h.
I have a question regarding that one first. What do we have RDT? Like,
Where is the 2dr?
not the underlying.
Next to the red.
Oh,
This is the h. One side is the h dt, and this is the r dt. What do you mean 2dr dt?
like, where did it come from?
I took the derivative over here. I took the derivative here.
Two times the derivative of r.
What's the derivative of r? It's 1, right?
Yeah.
dr dt. So 2 dr dt. And then I'm plugging in. I'm replacing 2 dr dt with dh. So these two that are underlined, as you can see, there is h that I copied. So there is h that I copied. Then there is 2 dr dt is replaced by dh, and then you have r, but r is 1/2 h. So they're all replaced at the same time. There are 4 things going on in that at that thing at the same time. What happened? Oh, it's tomorrow. Any other related rates, questions, issues, problems?
You just do like different types.
Which one?
What one's over? Like the sphere, radius changing, which one of those?
There's only one, and we did this in class. It was the spherical balloon. I did this one in class.
We can honestly just do. I just want to do more. Just let's see.
Yeah, but which one?
You want me to look back?
Yeah. Find something. No, it's still related rates. You were supposed to come here today with questions on related rates. And now next time it's fine. When I say come in questions, if there are no questions, I should just go with the quiz.
15.
Problem 15?
Problem 15, related rates. The melting snowball one. It's related. It's asking.
Beautiful.
Yeah.
can read it to you if you want.
I know all the letters. Let's see. It says a spherical snowball melts at a rate proportional to its surface area. Show that the rate of change of the radius is constant. Cool. A spherical snowball melts at the rate proportional to its surface area. All right. So, snowball is a ball, it's a sphere, that has equation for volume 4 pi over 3 r cubed, and the surface area is 4 pi r squared. A spherical snowball melts at a rate proportional to its surface area. Now, they say that the rate at which it melts. So first I have to find the derivative in respect to time to get the rate at which it melts, which in this case is 4 pi r squared dr dt. The sentence says, a spherical snowball melts at a rate proportional to its surface area. So that means that this is equal to k times 4 pi r squared, because when you are making two things proportional, you equal them with the constant k. That's the constant of proportionality. So now when you look at these equations, you have 4 pi r squared dr dt on one side, and you have k times 4 pi r squared on the other. All of these guys cancel, and you are left with dr dt is equal to k. Now that's constant, right? Done. K is constant. Some number. Yep. Done deal.
So, did it give us the K part of it?
No, it's constant of proportionality. We don't care what it is because it's just a constant. It's a value. That's all the problem wanted to know. That it melts at a constant rate. And it does.
It's basically just like
A proof.
yeah, okay.
You give us questions that are going to be exactly like the exam questions.
Exam will contain exactly exam questions. You're right.
No. You should give us examples that will be exactly like what would be on the exam.
Yeah, first of all, I have no clue what's on the exam. But definitely one or two of these guys. And they will all be from related rates. I promise that. I will not ask any chapter 4 questions on this exam. Yes.
So my whole thing with the K is that something we need to know? Not like that we need to know, like were we given the K part? Or do we just know to put K?
When you are in mathematics, no matter which course it is, since whatever algebra class, whenever you have a proportion, you are multiplying by a constant of proportionality on one side, which is k.
Okay.
So when a problem says things are proportional, you multiply constant on one side, doesn't matter which one. If they say they are inversely proportional, then you are multiplying by 1 over the variable. So this is now not calculus, this is algebra. Proportional. Okay, let's go actually write the wording. X is proportional to y mathematically is translated as y equals k times x. X is inversely proportional to y equals k over x. So this is something that are basics from algebra. So the problem says a spherical snowball melts at the rate proportional to its surface area.
Okay, so that's just
That means dv dt is equal to k times a. That's direct translation. A is surface area, yes. So the sentence that says a spherical snowball melts at a rate proportional to its surface area, the rate of the melt equals proportionally to, right? So equals k times a. Any other problems that you are interested in?
47.
47.
Oblique tracking.
Sounds fun, man.
This is a beautiful problem.
That's why I chose it.
All right. So that's the shore. We have a port. And we have a radar. And then we have a boat. So we know this angle is 45 degrees. I'll put the radar a little bit in because it needs to be like that. It's not a right triangle. And this is going to be angle theta. Call it the distance S. So a port and a radar station are 2 miles apart. So this is definitely 2 miles. A ship leaves the port at noon, traveling northeast at the rate of 15 miles per hour. So over here we have the speed, which is 15 miles per hour. So I'll call it ds dt equals to 15 mph, right, miles per hour. If the ship maintains its speed and course, what is the rate of change of the tracking angle theta, right, at 12:30? Does it say what time?
It says at 12:30 p.m.
Oh, ship leaves at noon. That's it. Because I need to know that time is 1/2 hour. I need something, right? So they said the ship left at noon, but they want at 12:30. From 12 to 12:30 is right, but it's in miles per hour, so I can't write 30 minutes. I have to write 1/2 hour. All right, so now they did give us a hint, which is but law of science solves this problem. What you might not remember from pre-calculus, and you should, if you have A, B, C triangle, the opposite sides are labeled as A, B, C. as well. And the law of sine says that A divided by sine A is the same as B divided by sine B is the same as C divided by sine C. That's law of sines, and you can use any of the two. So now when you look at your triangle, you see that you have this side over here on the shore to be 2. We don't have anything that is the length from radar to the ship. So the issue here is that I can use S and theta just fine. The problem is that I can't use 45 because I don't have the side across, and the angle on the top is not labeled. But we know that on the flat surface, and this is very small distances, so we can regard it as a flat surface, sum of all angles in a triangle is 180 degrees. If this was done over greater distance, that would not hold, because you can make some of the angles in a triangle to be anything if you put it on a curved surface. And this is on a curved surface, but as I said, this is only 2 miles, so the curvature of the Earth is not going to impact our calculation a lot. So we are going to regard this triangle as 180. Sum of all sides, sum of all angles is 180, which means that the top angle, right, is going to be 180 minus 45 minus theta. So this angle here is 180 minus 45 degrees minus theta, also known as 135 minus theta. So now if you look at your law of sines, you can say that length S divided by sine of theta is the same as 2 miles divided by sine of 135 minus theta. So now everything is changing, and we need to take these derivatives now in respect to time. So these are a little bit spicier derivatives, but still, right, we can use the quotient rule because S is changing, the length of how far, right? It's the speed of the boat. And sine theta. Theta is changing as well. So we use our quotient rule here. We say sine squared theta, then sine theta ds dt minus s times cosine theta d theta dt is equal to, and now on the other side you could do quotient rule, but you actually don't have to because it's a 2 on top, right? It's not a function, it's 2 constant. So you could just deal with this as sine of 135 degrees minus theta, right, negative 1. So you would have negative 2 sine negative 2 of 135 degrees minus theta times the derivative of the inside, which is negative d theta dt. Because when you take the derivative of theta in respect to time, and it's negative because there's negative in front of theta. So that was a little bit of a chain rule there. So all I need to do now is to fish out. I have everything, pretty much everything else. I just need to fish out this the theta dt. So sine theta, actually, you know what, it will be easier if you plug in what we know. So we don't know sine theta, so that needs to stay, sine theta. And then we have the s dt, that's the speed of the boat. We know that's 15. Minus, I don't know s yet, I don't know cosine theta yet. D theta dt is what I'm looking for. Everything divided by sine squared theta equals 2. Negative and negative will drop. So that's 2 over sine squared 135, oops, degrees minus theta. And then I have d theta dt.
Isn't d theta dt at the end of the second to last line negative?
Yes, because it's negative theta in parentheses. 135 minus theta. So when you take derivative of that, derivative of 135 is 0, and derivative of negative theta is negative d theta dt.
It's on YouTube right now.
Yeah. It's really cool. So sine squared theta can go to the multiply to the right. So I'll have 15 sine theta minus s times cosine theta d theta dt equals to, let's do it this way, 2 times, and then I have sine squared theta divided by sine squared 135 degrees minus theta d theta dt. So now, as you can see over here, you can simplify expression. You can use power reducing formulas to get rid of squares. They will bring in additional algebra. You also need to move the cosine term. Now, the only thing that I worry about here is the value for s. Oh, that's where we have a 30 minutes. So s is what? 15, so 7.5, right? That's half of 15. If you can travel 15 miles in 1 hour, then in 30 minutes you can travel 7 miles. So that's a 7 instead of s. That's 7. What happened? What happened?
7.5.
Oh, 7.5, yes. Thank you. 7.5. So that's what we have. Now, what I can do is we can simplify the formula on the right to get rid of the square by using the formula that you absolutely must know if you want to go into Calc 2. Power reducing formula says that sine squared of x is 1 minus cosine 2x over 2. So now we can use that here. 15 sine theta minus 7.5 cosine theta d theta dt. You can see that d theta dt needs to all go on the same side because that's what we are looking for. But I still have a lot of housekeeping to do over here. So the top would be, the 2 and 2 would cancel. So it's 1 minus cosine 2 theta, and on the bottom is 1 minus cosine of 2 times 135 minus theta. And then we have d theta dt. Divide the right hand side by Divide everywhere by 2 to get rid of that extra 2 over there. That's a half, so that's 15 over 4. It's easier to write it that way than to drag 5,000 decimals. There's a 2 there. And now we can bring this term to the other side to put d thetas together. This is a fun problem. Well, we might define fun differently, but and now you divide by the long thing. Now I'm wondering if we can simplify this further. Huh. No, this was much easier. All right. Oh, you're writing pen? Too bad. I just noticed that this thing right there is given here in a much simpler form.
Oh, 2 sine theta over s.
Yep. So it can be replaced and then canceled. So I'm just going to kill everything that I did. Ah. Yeah. So I'm going to kill these lines because we can make this much easier if we do that substitution from before. So I'll mark it with a star and probably do it in purple, and then we're going to so here we go. Here's the star. Put the star over here and write that equation. So sine of 135 degrees minus theta is equal to 2 sine theta over s. And now I'm going to plug that in here. So that's going to simplify everything much better. Sine theta minus 15 over 2, so we don't have to write the decimal. D theta dt, and now look what happens. 2 and so that's sine squared theta over. Now it was squared, so we are squaring the purple term, and we are getting 4 sine squared theta over s squared. Now we know s is 7.5. We still have the d theta dt. Now if you carefully observe, these guys cancel. These guys cancel, we get 2. And you see how much better this expression is now. That's a minus 15 over 2 cosine theta d theta dt. And over here I have s squared, that's 7.5 squared, so 15 halves squared over 2. d theta dt. There we go. Nice. So multiply everywhere by 2. 30 sine theta minus 15 cosine theta d theta dt is equal to 15 squared 225 over 4 d theta dt. And now just solve for d theta dt, put everything on the same side. So d theta dt, and what are we factoring? We have 225 over 4 plus 15 cosine theta is equal to 30 sine theta. And now you just divide by what's left. 30 sine theta divided by 225 over 4 plus 15 cosine theta. Now you can multiply top and bottom by 4 to get rid of the double fraction. And that gives us 120 sine theta over 225, the 4 cancels, plus 60 cosine theta. And there it is. Nice and compact.
Something like that gonna be on the test.
No, because this is, it takes a long time. Unfortunately, stuff like this, we don't have time for these
How unfortunate.
cool things, I would say. Exams are more like monkey sees, monkey do. That's like, you know, regurgitating unimportant stuff. Like, you will never be able to make any money with what's on the exam. If you really want to be an engineer or, you know, make money with these kind of things, these are types of problems that you have to work out because these are the things that you make money off. The rest of the sections is just, you know, stuff that we go through, and it's completely useless for you when you start working, like 98%. There are only 3 sections that are word problems, and that's what makes money. The rest are calculations, and Wolfram Alpha and Mathematica and calculators and computers can do that, and you will never be paid a dime to do it because a $300 computer can do it faster than you. There's no reason for anyone to pay you, you know, $70, $80, or $100,000 a year to do calculations. So what I just did is what makes money as engineer. The other stuff, no. At the end, if you want to figure out more of this answer, you would go to this equation here that is starred, and you will plug in the S as 7.5. You will solve that for theta, get theta to be whatever angle it is, let's say 73 degrees, I don't know. And whatever theta you get, you plug into this equation and you will have the actual number. Again, this equation is much more valuable than the actual answer because the answer just shows one snippet in time. If you are programming this, you actually have to program in the equation because the equation is the one that you program in and the equation drives the system. It's not a snippet in time. So if you need a time, you can always get the data table from the software or something for any of these. But the interesting thing for those of you who actually care about this stuff, you should program this to give answers. So that way, no matter what theta is, right? You're not solving the problem for the particular value. You're solving the problem with this equation for all values of theta. And then whatever angle the radar is at, you will know the rate of change and so on. That was a cool problem. Thank you. Like stuff like this makes my day. I don't know. Any other questions on related rates? All right, so today I guess those were the spicier examples of related rates. Make sure you know those formulas for volume and surface area. We did cone, we did sphere, we did triangles, we did trig, cylinder, cube. Awesome. Great. Well, that's it. I'm going to stop the stream and we'll restart with something else.